Next talk is by Harbir Antil. He's a professor of mathematics at George Mason, where he's the director of the Center for Mathematics and Artificial Intelligence. And he's speaking today about a novel approach to deep learning. Go ahead, Harbir, the floor is yours. Thank you.
Yeah, thanks, Colin, and also thanks to Eduardo, George, Anna, and Margarita for organizing this meeting. Lots of interesting talks, actually. So I'm not quite in this robotics community, but I will present some things that we've been working on for our last year or so. My background is more in partial differential equations and optimization problems with those partial differential equations as constraints, especially in infinite dimensions, and trying to design algorithms to solve those problems in infinite dimensions and then solve it after you discretize them. So, but what today I'll discuss is slightly different. It's some of the work we have done on neural networks and some of the applications. This work is partially supported by National Science Foundation, also Air Force Office of Scientific Research, and Department of Navy Naval Postgraduate School. So I will start with basically just a quick outline for my talk. I'll start with some motivation on why we are interested in these type of neural networks. And then I'll describe some of the existing challenges when it comes to neural networks. One thing we'll notice is that even if you've done training, I mean, we know this neural network problem is highly non-convex to start with, but even if you're done with training, still you have a significant non-uniqueness. I will describe what that means and how to overcome that, and also apply it to chemical reacting flow problems. And then I'll introduce a new type of neural network, which is ODE based, but I'll introduce some new terms that will allow us to create memory in the network and then apply it to Bayesian inversion problems. So a first motivation is we want to solve parameterized equations. It can be PDE or an ODE. So F is your nonlinear operator, U is the solution, and C is the parameter that, and you need to solve this problem for many parameters, or you may want to infer the parameter by solving an inverse problem. Example is Navier-Stokes, for instance, where Reynolds number could be the parameter, or Kosinets, where Grashof or Prandtl parameters, Prandtl number can be the parameters. In general, this can be a non-linear system, can be stationary or time dependent. That's not quite critical for the discussion now. So the challenge is that the space dimension for U can be really large. So this NX can be really large, especially when you're working with partial differential equations. You're talking about millions or billions of unknowns once you discretize the problem. And you may have to solve this for many different parameters, especially when it comes to inverse problems or optimal control problems. And you may need to have a significant amount of storage as well. And the idea is to try to replace this PDE by a neural network. So what really we need to learn is the parameter to solution map. This is a joint work with Howard Ellman from University of Maryland, College Park in computer science, a current postdoc of mine who will be joining Lehigh University actually in a month, Aku Manunta, and a former PhD student who just graduated, and he's joined Emory University as a postdoc, though he's spending his summer at Lawrence Livermore National Lab. The paper is available online. So this is about parameterized partial differential equations, or ODEs. The other application that we are interested in is also, this one is funded by DTRA actually. So here, what we are interested in is the so-called chemical reacting flows. And these chemical reacting flows are a coupled system of fluid dynamics equations like Navier-Stokes, and you need to couple them with some stiff ordinary differential equations. Currently, the solvers are spending more than 95% of their time in solving these stiff ODEs, and which can range from 50 to thousands. In fact, many of these problems are still open because we don't have enough computing capabilities despite of all the advances. The idea is try to replace these ODE solvers like called Camkin or Chamkin by deep neural networks. And I'll show you an example later in the talk that in many cases the neural network approach actually work reasonably well. This is a joint work with the current postdoc Tom Brown, Reinhard Lerner, who is the director of CFD Center here at GMU. Fumiya Togahashi applied, he is a scientist at Applied Simulation Inc. or ASI, and Dipanshu Verma, who I mentioned earlier. We have a couple of papers which are online. One just got accepted in this HPC conference, and the second one is currently in review. We just submitted last week. So we're basically talking about two type of problems. One are parameterized PDEs or ODEs, and then this stiff ODEs motivated by chemical reacting flows. So let me describe a couple of the challenges we have faced while we were learning these neural networks. So as I said, I started working on this just a little over a year ago. And let me give a quick outline of what a neural network looked like. We have seen some of these things in some of the talks earlier, so the goal of a neural network is you want to approximate an input to output map using this operator, call it calligraphic F, which can be written as a composition of these layer functions. And these layer functions depend on your weight matrix and your bias vector. And of course, that gives us a linear transformation, and then you apply a nonlinear activation function, for example, a ReLU. So that's how a typical neural network look like. So this is a rather generic for the moment. I'm not assuming any particular structure. It can be that ODE net that we discussed, that was discussed earlier in the afternoon. And then you need to train the network. One goal is to identify these weights and biases. And how do you do that? In supervised learning, typically you're given some input data, let's say UI, and some data that you're trying to match with the output of a network. So this becomes a constraint optimization problem. So you're trying to match the output of your neural network with some observations that you have made. And you're trying to identify the parameter theta by solving this optimization problem. So that's basically your optimization problem. And once you have identified these parameters, then you basically go and evaluate this nonlinear operator, because you know all these F, what these are, and then you do predictions. A typical example of a loss function is your standard regression function, for example. It could be logistic regression also. For the type of problems that I will describe, logistic regression does not make so much sense. It's more for classification type problems where you have probabilistic interpretation. And you can add some regularization also on the weights and biases, for example, the L1 regularization or L2 regularization. So that's a structure of a typical neural network. Now, one issue is, so let's say you have a network with two hidden layers, one input, one output, and these dots indicate biases, a component of the bias vector. So what we notice is that in this second layer, I can exchange, even after training, this A and B, and we can do many of these permutations, right? So even with this network of two layers, I have thousands of possible perturbations. The network remains the same, but the solution changes every time I do this perturbation. So there is a significant amount of non-uniqueness, which for some reason was not really mentioned in the literature until we came across this actually a few weeks ago, and then we wrote the paper. So the question will be, how do you address this type of non-uniqueness? And then you take a step back. Can you lower the dimension of your parameter space in some ways so that you can do some fast training. I'll come back and show you how to address this at least one way. So the other issue is which neural network face, and there are many approaches to tackle this, is the so-called vanishing gradient issue. So let's just look at the black solid curve and the black dotted curve. The black dotted curve corresponds to the magnitude of the gradient with respect to the parameter in the first layer, and the black dotted curve corresponds to the magnitude of the gradient with respect to the parameter in the in the last layer, and they differ by 2 orders of magnitude. But this causes problem when you're trying to do training, because it will make your parameters may not update, and your whole training might stall. This is what they call vanishing gradient problem. I'll describe a mathematical formulation on how you can overcome this. And what you will observe later on is that you get a result like this dotted red curve and the solid red curve using this new approach, which I'm going to discuss later on. And the typical another issue that we're trying to address here is that typical neural networks are meant for classification, but we are interested in replacing our PDEs and ODEs by neural networks. So let's focus on the first issue, which is the non-uniqueness, where I mentioned I can do this perturbation or permutation of those bias vector components and get a different solution, keeping the network fixed. So how do we address that? This is what I had shown earlier, which was a typical neural network problem. Now I'm introducing a new thing, which it didn't exist in the literature earlier, at least when it corresponds to neural network. What I'm going to do is I will introduce an ordering on the components, the bias vector in each layer. So in each layer, bias will be ordered if I enforce these inequality constraints. Of course, you may say now you're making the problem harder. Yes, but one way to realize this inequality constraint is by penalty approach. So here I'm calling the Mori-Yoshida penalty regularization, which is a more generic term. But you can easily prove that actually as gamma goes to infinity, then you really satisfy these inequality constraints. And in practice, in our examples, we notice that you don't have to take gamma too large. 100 or 1000 is enough to have a reasonable ordering, actually up to machine precision. And the key advantage of using this formulation of enforcing the ordering is that you can easily integrate, you have to write a few lines of code in your existing PyTorch or TensorFlow libraries. So that's an idea basically on how to do ordering for biases. Then you are fixing your parameter search space, and you're not allowed to do those permutations any longer, because if you do those permutations after you have ordered them, then you will not get ordering in the end. So the idea is applicable to actually any neural network at this point, because I did not assume any structure. In the examples that I'm going to show next, we work with a ResNet type architecture. And again, the previous idea is independent of a particular architecture. Here we have an input, call it C. And this equation, in fact, has a representation in the continuous sense. So this is just simply a forward Euler discretization of an ODE. And I'll come back to this point actually and introduce a new type of network. So now let's apply this ordering idea to an example. So very, very basic example. Just we want to learn a function sin x. So, and we have 2 hidden layers, and each layer has 50 neurons. So that's the width of each layer. And we set that regularization parameter gamma to 100. And we generate that data using 1,000 evenly spaced points on the interval 0 to 2 pi. We use 400 points for training and 200 for validation and 400 for testing. We clearly notice that in the first case, where we did not have that regularization, we don't have ordering for biases. So here dots represent bias. Different colors corresponds to different magnitude. Lines corresponds to the magnitude of the weight matrix. Now we turn on the regularization with regularization parameter 100, and all of a sudden the biases are ordered. So we are enforcing uniqueness in our network. So which is pretty good actually. Even the magnitude of the overall bias, the range is larger than what we had previously. So your network is supposed to do well, right? Because you have less redundancy. And in terms of the actual function, so again, a very, very simple example. This is, so blue denotes the original function that we're trying to match, and red dot is the neural network approximation. We notice that in the classical ResNet, we are missing one of these bumps, right? The inverted bump. And the error was on the order of 10 to minus 2. But if I do this ordering, apply the ordering idea, then we get a pretty nice recovery, and the approximation error is one order smaller. So we are gaining an order in terms of approximation error. So overall, it does not sound like a bad idea. Then we applied it to that chemical reacting flow example I mentioned earlier, which is a much more challenging example. So here we are working with a simpler model of hydrogen-oxygen reaction. We have 8 species and temperature. And what we do here is we train 9 parallel residual neural networks with input dimension in each network is 10 and output is 1. And we train corresponding to data set corresponding to initial temperature of 1200 Kelvin, 1500, 1800, 2100, and 2400. And what we are learning here is solution at the next time step. And we do testing at 1400 and 2000 Kelvin, which was not part of your training, of course. And this is a very challenging problem. You can see from the scale on the x-axis. So these reactions takes place rather quickly. So you'll be like, nothing is going on, then all of a sudden it shots up and then it comes down. So these happen extremely fast, and it's really hard to catch actually. That's why people, when they implement these ODs, they end up in implementing explicit schemes to capture this. Or if they do implicit, then it takes a little time, right? Because you need to solve nonlinear equations by Newton's method or something. So here the blue, so this 9 figures on the left corresponds to 1400 in Kelvin. That's the initial temperature was. The right one corresponds to 2000 Kelvin. Blue curve corresponds to the actual solution. And the red dotted curve corresponds to the neural network approximation where we did not do ordering for biases. Black dotted curve corresponds to where we did the ordering for biases. And we really notice a significant difference actually. All right, so we're pretty excited about this idea actually. But now I'm gonna switch gears and come back to that inverse problem that I mentioned earlier at the beginning of the talk. So remember, we had this this parameterized PDE or ODE, and we have to solve this many, many times over. I want to replace this by neural network. So the goal is to try to approximate this parameter to solution map by neural network. We need to generate some training data. So let's say this, we have different realizations of the parameter and the corresponding solution to the PDE. That's our training data. Then we do a neural network approximation. We already saw this earlier, and here I've written it particularly for a residual neural network, or how the structure looks like. So in the end, if you can identify these weights and biases, then you don't have to go back to PDE. You can just plug in a new parameter and get approximation of the solution. So that's the idea. And if you have to do inversion for parameters using, let's say, Bayesian framework, then it'll be much cheaper to evaluate this rather than trying to solve this PDE, because this only requires computing matrix vector products and applying a nonlinear activation function component wise. So you can identify the parameters by solving a constraint optimization problem, right? I already discussed that previously in the generic setting. Now, this middle equation here, I mentioned earlier that this can be thought of a time discretization of an ODE, right? But what's happening here is that one layer is connected to the next, and next one is connected to the next, so on and so forth. What I will do is I'm going to replace this ODE by a different type of ODE, by a fractional ODE. Here, instead of the standard time derivative, we have now a fractional time derivative. And the key advantage is that this is a non-local operator and it builds in memory. So your layers, the first layer will be connected to the second, and third layer will be connected to the second as well as the first layer. So you have connections between all the layers. And we noticed in our numerical experiments that helps with training. The network trains faster, and it also helps with your vanishing gradient issue. And that's how this fractional time derivative look like. And you can see if you want to evaluate this object at a point t, it's not a local difference quotient, but you really need to compute this integral operator. In terms of implementation, it's not too hard actually, rather easy to implement. All right, so I showed you this picture at the beginning of the talk, and we really see that the solid curve is close to the dotted curve in comparison to the standard ResNet, which is the black curve and the dotted curve. These are the magnitude of the gradients in the first and the last layer. You can find details on this in specific to classification type problems in this machine learning and science and technology paper. But we further extended these ideas to Bayesian inversion problems, where you're given some noisy measurements and you're trying to invert for the parameter C. This is a challenging problem, especially when U corresponds to solution to a partial differential equation, because you have to do many PDE solves. And if you're nonlinear PDE, it can be quite expensive. So let's consider two examples. The first one is rather simple. You have the standard diffusion equation, diffusion PDE, delta is a Laplacian, U is some concentration or some temperature, and you have a nonlinearity of exponential type. And we have working with two parameters, xc1 and xc2. Here is when we do inference using Bayesian inversion, we get this histogram for the parameter C1 using the full model where we do PDE solves, and C2 is the second parameter. The actual parameters are 1 and 0.1, and that's where they are centered. And the right column corresponds to the solution where we did not solve the PDE, but we use this neural network approximation. CPU time, in terms of the full model, it took around 40 minutes, and this DNN, the deep neural network approach, it took like 2 minutes. And this 2 minutes also includes the training time. For this example, it was pretty fast actually due to the training. The second example is a little more involved. We're trying to figure out this permeability coefficient C in your diffusion equation. Part of the boundary, we are enforcing standard Neumann conditions, and the other part, we have the Robin type boundary conditions. So, and we are making some observations on the boundary. From those observations, we're trying to infer this permeability field inside the domain. So that's the problem. I don't have so much time to get into further details. Just want to emphasize that the gain in time is significant. Actually, the full model took 3 hours, and the neural network model, it took like 18 minutes to invert for the parameters, and the accuracy was not lost. So I just want to summarize that are motivated by parameterized partial differential equations, inverse problems, and chemical reacting problems. We have introduced or we have taken a new look at neural networks, which are optimization based. That's been always our motivation. We've looked at the known uniqueness in neural networks. We fixed that by ordering biases and incorporating inequality constraints. We've also looked at this vanishing gradient issue where we introduced this fractional deep neural network or the non-local deep neural network. And I have applied it to a couple of problems in Bayesian inversion, chemical reacting flow. We also have some analysis results, but I didn't want to bore you guys with those in my talk. We have a couple of papers that we recently put out, which are on archive, and one has been accepted, the last one. Yeah, thank you very much.
Thank you, Harbir. Very good. Very interesting. Do we have any questions? George.
Thanks, Harbir. Sorry, really interesting talk. So regarding the Bayesian inverse problem, you applied in the context of PDEs, but if you were to apply it in the context of ODEs, and specifically for the scenario that Annie was discussing earlier today, where you want to learn the dynamics of a system of agents, can you cast your solution, or can you cast the problem in a way that you could apply your approach to it and learn, for instance, in a noisy environment, do this kind of Bayesian inversion with the type of framework that you have?
My first impression will be definitely, because here also we are working with noisy observations, and we basically approximate the PDE by neural network, and then we just have noisy observations. That's what I call Y, which was U plus some noise. So seems like the setup is very close actually, and I believe this can be done. I mean, there are some details that needs to work out, but I do not see a major challenge. Once we learn those dynamics, we should be able to replace your ODE model basically, and then just use those learned dynamics and couple with our framework.
Excellent. Yeah, that sounds like maybe a good thing to talk about offline with Annie as well. So yeah, thank you.
I'll be really curious actually.
Anyone else? Okay, I had just kind of a curiosity. When you have your fractional setup, you talked about that the layers are communicating with each other, so it's kind of like a skip connection, right?
It's on top of skip connection. There is more going on. It's like a dense net actually.
Okay.
Yeah.
And then is it the first that communicates with all the others that follow, or are you having information going backward? Is the third one tied, is it a two-way communication essentially?
So when you do forward propagation, then it's one way, it's just forward. So the third layer will get information from the second as well as the first. But when you back propagation, then yes, the information is going the other way also. So we are doing both. So I didn't get into too much detail, but the way we are solving this neural network problem, we're really using NLP type approach where we solve the state equation, the adjoint equation, and then compute the derivative. And the state equation is your forward equation in time. It's the same when you work with a standard ResNet or with the skip connection or with the fractional DNN. There's the ODE looks different and discretization is different. And then the adjoint equation is your ODE, which is backward in time. So there, the information will be going in the other direction.
Are you able to control kind of the degree of connection between the layers? Like, is there a way to scale that or weight it?
Right, it's actually weighted. That's a good question. So it's actually weighted. There's a polynomial weight. So if you go really far, that so it decays it decays polynomially. What the contribution will be from far away nodes, but you could try and use an exponential kernel here, where yeah, it depends on how much connection you want.
Thank you.
Yeah.